Welcome back everyone. In this lecture actually we will see the proof of the invariance lemma, which is a crucial result which will be used to prove the Engel's theorem and Lee's theorem and so on. Okay. So, this is a very important formalization. Okay. So, let us actually state the invariance lemma. So, before stating that I need to actually fix some terminologies. Okay. So, we call so let us start with the Lie subalgebra linear Lie subalgebra. So, let me denote it by capital A. So, let us say capital A is being linear Lie subalgebra. Okay. So, why I want to actually restrict to this situation? So, I want to have all the elements of capital A acting on this capital V. So, we will see later the notion that I am going to define now called weights that can be defined even for any representation of any arbitrary algebra. But anyway, let us do it in this special situation and then later we actually explain, I will explain how one can do it for the general representation. Okay. So, what is a weight? So, a weight, so this is the somewhat important notion that will actually pop up a lot in representation theory. So, a weight for A is a linear map lambda from A to C such that this V lambda which I am going to define. So, it will be called weight space. So, those V in capital V such that A V, so A acting on V should be equal to lambda A V for all A in capital A. Okay. So, this should be a non-zero subspace of capital V. Okay. So, you call a functional. Okay. So, lambda being linear map from A to C. So, then we can call lambda is in this A star which is the homomorphisms from A to C. And so, this is actually a weight if you define what is called this weight space. So, this weight space should be non-zero. Okay. So, this V lambda, so this will be called weight space, of course corresponding to the weight lambda. Okay. So, let us fix some notation as we said. Okay. So, this A star we use very often. So, this is actually all the homomorphism from capital A to C. So, that means this is all linear homomorphisms, not algebra homomorphisms. Okay. This is all set of all C linear maps. Okay. From A to C. So, now in terms of that, what is on weight? So, weight is an element of A star and then you can, so for any element of A star you can define this weight space, okay, which is V lambda such that you collect those V in V such that A V acts as lambda A V for all V in V. Okay. So, this should be non-zero. So, you can define V lambda for any lambda, but you call lambda weight if and only if this V lambda is non-zero. Okay. So, now let us actually state the invariance lemma and then I will try to motivate actually why one expects such a statement and then we will see the proof of that invariance lemma. Okay. So, here is the invariance lemma. As the name suggests, this is actually about some invariance of some subspace. So, let us see what it is. So, we work over complex number, in particularly So, this is characteristic 0. So, you can also take any characteristic 0 field, not a problem. Of course, if you assume algebraically closed field, then we can talk about all these eigenvalues and so on. So, that is why we are working over complex numbers. So, you start with a Lie algebra, which is a subalgebra of some GLV. Okay. So, let G being linearly subalgebra. So, where V is finite dimensional. Okay. So, V is finite dimensional and take A being ideal inside G. Okay. So, then let lambda be a weight of A. Okay. So, let lambda be a weight. So, now what we can do, we can actually construct the corresponding weight space, okay, and then ask. So, this is obviously A invariant. Okay. Now, the question is, since A being like a special subalgebra of G, you can ask whether this V lambda is actually indeed G invariant subspace or not. Okay. So, you take this V lambda, which is those V in V such that AV equal to lambda AV for all A in A. So, we prove that this is indeed a G invariant subspace. Of capital. So, this is somewhat very important observation. Okay. So, you may ask actually, so where such a result is actually coming from or the observation is coming from. So, if you go back and then recall some of the results that you have seen in the linear algebra. So, that is what motivates us to actually state something like this. So, for example, let me state it in very generality. Okay. Suppose if you have two operators acting on let us say V, assume that A B and B A they commutes, okay, A B equal to B A. Okay. So, then what we can do, we can talk about lambda eigenspace of A. Okay. You take V lambda, so that to be lambda eigenspace of A. So, what is the definition of V lambda? V lambda is nothing but those vector in V such that when you apply A to that V, you get lambda A or just lambda, okay, because there is only one operator lambda V. So, then from the linear algebra you can see that because A and B they commute. So, you can prove this. If you have not done this exercise, you should do. One can prove that this V lambda is actually B invariant. So, what is the meaning of that? If you start with the vector V inside V lambda, then BV will be again lambda eigenvector corresponding to the eigenvalue lambda. Okay. So, it is actually a simple check, maybe let us do it now itself. You start with V inside V lambda, then you want to compute what happens to BV. Okay. So, what you want to do? You want to see when you act A on BV whether you get lambda BV or not. So, you just compute ABV and then see that this is nothing but BAV because AB BA they are equal. So, now AV is being lambda V, if you substitute back you get B lambda V. So, then it will imply lambda into BV. So, you proved that ABV is equal to lambda BV, that means BV is being again inside V lambda. So, this is somewhat very important observation because if you think in terms of Lie algebra. So, this if you take the span of AB, that is actually gives you the abelian Lie algebra. So, then this subspace span by A gives you ideal inside that. So, indeed when you construct this weight space corresponding to this ideal. So, you are saying that that will be invariant under entire space. Okay. So, that is what hidden in this exercise. So, this is not very hard to actually generalize for any family of commuting operators. Okay. So, that maybe I will leave it as exercise. So, what one can prove, suppose you have a family of commuting operators, call it AI, I in I, okay. Let us say family of commuting operators from, let us say, endomorphism, okay, acting on the same space. So, now what you can do, you can talk about like lambda eigenspace for some particular actually particular operator. So, if you take for example AI, so you can talk about lambda eigenspace of AI. So, let me call it V lambda. Okay. So, then one can prove that this V lambda is invariant under any other AJ. So, this is something very important observation. So, this is just follows from what we have seen earlier. Okay. So, basically that is what I have written again. Now, such a phenomena is actually holds in our setting as well. Okay. You have G which is a subalgebra of GLV, and then if you have ideal A inside G. Okay. So, then you can talk about weight space for the weight of this capital A. So, take lambda in A star and then take V lambda to be those V in V such that A V is nothing but lambda A V for all A in A. So, our claim is this V lambda is G invariant. Okay. If V lambda is 0, then nothing to prove. So, we only worry about the weight space for which V lambda will be non-zero. Okay. So, what we need to really prove? So, you start with some vector V in V lambda and then some y in inside G. Okay. So, for V in V lambda and y in G. So, if you compute this y v, so we want to say that, so we need to prove, let us write it here. We need to prove that this y v is again in V lambda. So, equivalently, so if you apply A on this y v, so we should get exactly lambda A of y v, okay, for all A in A. So, that is what we need to prove. But let us see like why you indeed actually get something like that. So, here is the trick. Okay. So, if you compute A y v, you can see that inside the Lie algebra A y is nothing but y a plus some error term. So, that is the commutator which is just A y. Okay. So, the bracket y A y is equal to A y minus y a. So, in particularly if you rewrite A y, so which can be written as y a plus A y. So, this is true inside, you can think inside either endomorphism of V or inside the subalgebra, associative subalgebra generated by capital G, sorry G and so on. But anyway, this is true as an operators. So, in particularly if you compute this A y v, so you get y of A v plus the bracket A y of v. Note that A is coming from capital A and then y is coming from G. So, that implies this A y is in capital A as A being ideal inside G. So, that means, so this is inside capital A. So, then this equation can be rewritten A y v equal to, so A v is lambda A. So, lambda A y v plus lambda a y and then v. Okay. So, now if you want to show what we expected to show, this a y v is same as lambda a y v for all a in A. So, we need to prove that this term which we are getting it from the error term. So, this part must be 0. Okay. So, you may ask like why such a term one can expect to be 0. If you think about it, this is actually commutator. Okay. What is bracket a y? So, let us try to work backward. So, what I mean by that? So, what we need to prove? We need to prove that this V lambda must be must be G invariant. So, this V lambda, suppose if it is G invariant, then what will happen? So, both this y will act on V lambda. So, this y will act on V lambda and already this A is acting on V lambda, okay, that is acting as scalars. So, if you put together, then what will happen to this commutator? The commutator will again act on this V lambda. Okay. But we know that trace of any commutator will be 0. So, if you restrict to V lambda, so that will be trace of A restricted to V lambda times y restricted to V lambda minus A restricted to V lambda times y restricted to V lambda minus y restricted to V lambda times A restricted to V lambda. So, that implies the trace of this A y must be 0 when you restrict on this V lambda. Okay. But what will be the trace? So, this A y, it is an element inside capital A, okay, because it is an element in capital A, each element of capital A acts as scalar. Okay. So, each element A acts as lambda of A on entire space. So, that means if you compute the matrix of this A with respect to some basis, so that will be just a scalar matrix with the diagonal entries lambda of A. Okay. So, it is clear that for any z in capital A, if you compute the matrix z, so this will look like something like this, lambda of z, 0 elsewhere. So, that means the trace of z restricted to V lambda. So, that will be actually the dimension of V lambda times lambda of z. Okay. So, now if you take z to be the bracket a y, then you can see that the trace of the bracket a y restricted to V lambda will be equal to dimension V lambda times lambda of a y. Okay. Since this trace is 0 as a y being the bracket a y being commutator. So, you get the dimension of V lambda times a y is 0. So, now V lambda is being non-zero space, the dimension is being non-zero. So, that would imply lambda a y is 0. Okay. So, that is why one can expect this lambda a y being 0. So, if we prove that this is actually 0, so then indeed it proves that this V lambda is G invariant, and we by working backward we could see that this is being G invariant is also equivalent to saying that this lambda of a y is being 0. Okay. So, it is actually somewhat inbuilt. So, and it is natural to expect from this work backward idea. Okay. So, let us see how one can actually prove such a result. So, what we need to prove? We need to prove that for A in capital A and then y in G, if you compute lambda a y, that should be 0. So, note that the bracket a y is inside capital A. Okay. So, indeed if you think about the argument that we actually see in this work backward, all we needed is some y invariant subspace. Okay. As long as we have the y invariant subspace and then A invariant subspace, we will be able to actually calculate this trace of bracket A y, which will be 0. So, in order to produce y invariant subspace, so there is a natural subspace called cyclic subspace. Okay. So, that is what we will take. So, what we do, we take this U to be the span of this V, y v, y square v, etc. Okay. Since U is actually inside your vector space V, which is actually finite dimensional. So, that would imply that U is also finite dimensional. So, now what we can do, we can choose small k. So, we can choose small k in Z plus such that this V, y v, etc., y power k v is actually linearly dependent. So, that would imply that v, y v, etc., y power k minus 1 v. So, that will be linearly independent. So, that means, so this is just a simple exercise from linear algebra. I will leave it to you. You can see that this set v, y v, etc., y power k minus 1 v. So, that will form a basis for this capital U. Okay. So, note that where is this v is coming from. So, this v is already coming from v lambda. Okay. So, we have chosen this v is from v lambda. So, then if you actually put together everything. So, this v is in v lambda. So, in particularly we have constructed y invariant subspace. So, which is span of this v, y v, etc., y power k minus 1 v, that is inside your ambient space. Okay. So, this is clearly y invariant subspace. Okay. So, now we just check whether it is actually A invariant or not. If it is A invariant, then from our earlier argument, it is clear that the trace of bracket A y restricted on U will be 0. Using that, we will be able to actually compute the lambda of bracket A y. So, that is the idea. So, let us see how this A acts on this U. Okay. So, let us compute how A acts on this capital U. So, now just actually look at A v. So, A v will be just lambda A v. So, by definition, because v is coming from v lambda. So, now if you take A y v, so then what happens A y v, if you recall the formula. So, this is just actually indeed we can actually check for any element of capital A, not necessarily for just A. So, for that let us take how capital A itself acts. Okay. So, then I want to compute some z in capital A, how it acts on U. So, if you just look at it, z v will be just lambda v, lambda z v, because v is coming from v lambda. So, if you compute z y v, so using the earlier formula, you can see that this is y z v plus that bracket y z. So, if you just write it again, so this is bracket z y on v. So, that means this is lambda z y v plus lambda of z y v. So, what is important, if you compute y v, so this is actually inside lambda z y v plus lambda z y v. So, this is inside the span of v comma y v. Okay. So, let us see whether this is accident or this is what happens for higher powers. Okay. So, let us compute how it acts on y square v. Okay. If you compute what happens to the y square v, so we can use what already how it acts on the y v. Okay. So, this is going to be again y v z y plus bracket z y and then acting on y v. So, that means z y square v is nothing but z y square v plus z y y v. Okay. Sorry, what I have written. So, this is supposed to be y z. Sorry. So, z y square v. So, I am writing it as z y acting on y v. So, this should be y z plus z y acting on y v. So, that means z y square v is nothing but y z y v plus the bracket z y y v. So, then just to unravel, you already know how z y v acts. So, z acts on y v as y into lambda maybe z y v plus lambda z y v plus z y y v. Okay. So, now you can see that. So, this is nothing but lambda z y square v plus lambda z y y v plus z y acting on y v. So, now since this z y is again element of capital A. So, for any element of capital A we have this formula again. Okay. So, this is going to be on y v will be some span of v comma y v. Okay. So, whatever it is, it does not matter. So, this is going to be inside span of v comma y v, and here you can see that z y square v is nothing but lambda z y square v plus all the terms that are coming from lower span of lower terms v y v. Okay. So, basically this is all matters for us. So, z y square v is nothing but lambda z y square v plus some term, that some term is coming from span of v comma y v. Okay. So, because we are interested only in the computation of trace. So, that is why we are looking at what happens to the diagonal entries. Okay. So, now I will leave it to you to check. So, this is not very hard. The same computation actually tells you that if you compute z y power r w, so then you can claim that. So, this is actually equal to lambda of z y power r w plus some term u, where this u will come from span of v, y v etcetera y power r minus 1 v. Okay. So, in particularly if you look at the basis. Okay. So, what we have seen. So, this is this is y v. So, basically what happens. So, if you take this basis v, y v, y square v and so on. So, y power. So, let us what is the power we have actually fixed. This is k. So, y power k minus 1 v. So, under this z where it goes, you can see that. So, this goes to v goes to lambda z v, and then y v goes to lambda z y v plus something coming from span of v. Okay. Similarly, for the rth power it goes to lambda z y power r v plus some term, that term comes from span of v etcetera y power r minus 1 v. So, similarly for this lambda z y power k minus 1 plus some u, where u is coming from span of v etcetera y power k minus 2 v. So, that means if you just write down the matrix of z with respect to the basis, okay, this is the basis that we are taking. So, the basis to be v etcetera y power k minus 1 v. So, then you can see that this matrix looks like lambda z and so on, lambda z, here some stars whatever it is does not matter, and then 0. Okay, this is just a upper triangular matrix with the diagonal entries being lambda z. Okay, so that means, so what is the trace? The trace of this z on this acting on this capital U. So, that is nothing but the dimension of u times lambda of z. Okay. So, there are few observations. First observation is so this first observation is z is actually leaving u to u. Okay. So, that is the first observation. The second observation is the trace if you compute. So, that is exactly comes as expected value, dimension u times lambda of z. So, this equation tells us that z is acting on capital U, okay, because this element is also in capital U and then this element is also in capital U. So, from the explicit computation we see that z actually leaves u invariant and the trace is nothing but dimension u times lambda of z. In particularly the element that we have chosen capital a from capital A and then y from G, you can see that this u is actually invariant under both A and y. So, u is invariant under both A and y. So, that means if you compute the trace of this A y which is an element inside capital A, you get with respect to the basis B, you get dimension u times this lambda bracket A y. So, which is 0 because both A and y leaves u invariant. So, this is commutator. So, that will imply lambda of bracket A y is 0. Okay. So, that completes the proof. So, basically what we did, if you recall, so if you go back to the proof, so basically what we did, we started with some elements A and A from capital A and then y from G and then we fix a vector v in v lambda. So, what we wanted to do, first we wanted to compute some y invariant subspace generated by V. So, that is why we just looked at this cyclic subspace generated by this vector V under this map y. So, that is the span of V y square V etcetera. So, then it is a simple fact from linear algebra, there exists a small k such that this V y V etcetera y power k V is linearly independent, but this V y V etcetera y power k minus 1 V is linearly independent. So, this is dependent, this is independent. So, that means this makes a basis. So, now you compute for any z in A how the action of that z on this subspace. So, you compute it on V, y V etcetera and then you see that if you act it on y power r V, z actually gives you lambda z y r V plus some element that is coming from the lower degree term in some sense. It is coming from the span of V, y V etcetera y power r minus 1 V. So, that way we are able to compute the trace and then we could see that this trace is 0, okay, because for both A and y, this both A and y leaves this capital U invariant. So, that makes this trace actually 0. Okay, so this completes the proof of invariance lemma. So, in the next lecture we will see some applications of this invariance lemma. In particularly we will prove the Engel's theorem and Lee's theorem. We will stop here. Thanks.